Okay, so each of those critical points in the parent graph, the 1, 0, the 4, 1, and the asymptote are all going to be horizontally reflected due to the negative sign, and then shifted up 3 due to the plus 3. So starting with the vertical asymptote, when you horizontally reflect that over itself, over the y-axis, it does not move. And then when you shift it up 3, it does not move. So that's good, right? We're not moving that. Flip this point horizontally and then shift it up 3. Shift this point, or flip this point rather, horizontally. It's 4 units to the right, so flip it 4 units to the left and then shift it up 3. And we go towards negative infinity when we go towards the asymptote. So here we have g of x, and here we have f of x. Any questions on that? Okay. So on a different type of function, without having, maybe we'll end up sketching it anyway, but let's try to see if we can avoid it. We have a different parent graph. So what is the parent graph of that function? What is the equation? I'll call it p of x. Log base 2 of x. Good. And what is the domain of that parent graph? What x values are you allowed to plug in there? Taylor? No, not this one. I'm talking about this one. Not including 0 though, right? So x is greater than 0. We'll go that way with it. And the range for a log parent graph is, right, all real numbers, negative infinity to infinity. You can see from this parent graph up here, negative infinity to infinity. So on the transformations, we've got something happening horizontally, which is going to change what? The domain or the range when we shift horizontally? Domain. So we're shifting this left 3. So our domain is going to be moved left 3. So our domain is going to be x is greater than negative 3. And our range, the vertical movement was a vertical reflection. If you reflect from negative infinity to infinity, you're still going to have negative infinity to infinity. So our range will not have changed. Okay, so you can get the domain and range from the transformation thought process off of the parent graph. Or, Taylor, I'm guessing that you thought you can only take the log of a positive number, so you knew that x plus 3 had to be greater than 0? Did you think of it that way, or did you do it the transformation way? Or a different way? Because you got that pretty quickly. Were you thinking along the lines of transforming the old domain, or were you kind of thinking, oh, we can only take the log of a positive? Oh, you were. Okay. And that's fine. That's kind of the visual look, but right, well, like we talked yesterday, you can only take the log of a positive, so x plus 3 has to be positive, and then when you solve that, you get the same domain. Correct. Right, it'll just make it steeper, but still negative infinity to infinity. And the same is true of thinking about inverses. For exponential functions, domains will always be negative infinity to infinity. Does that make sense? Any questions on any of this? Okay, the common log, unlike the natural log, we talked about the natural log yesterday with a base of e. The common log, when you just see log, has a base of 10. So just pointing that out. And just out of curiosity, what does this equal? 3. So if you don't have a base on your log, just to review, we know it's 10. What do we have here? Percentage of adult height attained by a boy who is X years old can be modeled by f of x equals 29 plus 48.8 log of x plus 1. Approximately what percentage of his adult height has a boy attained by age 10? So they're giving us age 10, so where are we plugging in the 10? X, we're looking for f of 10. And this would be a calculator question because you don't know the log of 11, right? Plus 48.8 times log of 11. 79.8. So approximately what percentage? Let's round it to the nearest tenth of a percent. 79.8%. Now I'm curious. How old are you all? 16. So what is going to be, let's think about what your full-grown height would be if this model were correct. Won't that be fun? So take a minute, using this model, figure out what your full-grown height will be for you based on your current age. Now, if you want to be more specific about your current age, you can make it like to the nearest 3/4 of a year. I'm going to do the same for myself. So figure out what your X value equals. Plug it in. Get your percentage of your adult height that you are right now, and you. How old are you? What month? Were you born in May? So your X is 16.5. I'm doing, well, you guys are doing yours. I'm going to do Liz's. She's 16 and a half years old. So 8.8966 of how tall are you right now? 5 feet 5 inches. So 5 feet 5 inches equals 65 inches. So I don't believe it. This model's a farce. So first of all, let's understand. Were you able to do the math? 6'2", Liam?
Yeah.
There's hope. Well, first of all, oh, this is a boy. This isn't really going to work for girls. Oh, see, if Liz was a boy, then she would be. That might work. I I know. I know. I feel like this model tops out at like age. Well, at any rate, just to wrap our head around, make sure you are understanding the math properly. If you're 16 and a half years old, that means that Liz is currently 89.66% of her adult height. So that percentage of her adult height, and this is her current, right? Right now she's 89% of her adult height, which is, she said she's 5'5", so 65 inches, and then if you divide both sides by 0.8966, that gives you her adult height of 72.5 inches, which puts her at 6 feet and a half of an inch. So we don't believe it. But I think if I graph this, 29 plus 48.8, my mom told me you're supposed to double a kid's height at 2, and that gives you a good approximation of their adult height. No, I did it with my son. He, what was he? It's like 3 feet, 2 and change. Like just under 3 feet tall, I would say. I'll tell you, I marked it on the measuring stick at home, so I will tell you. And I doubled it, and it was not bad. Well, first of all, you should see how they measure babies. It's the least exact method you could possibly imagine. They put you down, they put the baby down, they mark his foot, they kind of try to make him straight, but they're babies, so they're wiggling, and then they just, they throw something on the paper, and then they measure the paper. It's like ridiculous. So I don't really buy any of that anyway. But for the record, our X is our age, so I'm going to go 0 to 20. And our Y is our percentage, so I'm going to go 0 to 100. And so here's what your log graph looks like. And so the older you get, you're obviously growing faster earlier, but by the time you get near age 20, you're pretty close to 100% of your age. Or 100% of your height. So it does, the whole log concept, the fact that it evens out and flattens out seems like at least one of the better models, right? Growing quickly at first and then evening out. However, at age 33 and a half, I have achieved 104.04%, which I think means I am, how would you interpret that? No, I've grown. Oh no, I took it as like I've already grown to my 100% and I'm actually shrinking. Huh? Oh, that absolutely happens. I think I've already shrunk, and I'm not even kidding. I think I've shrunk. It is all in the vertebrae. Bringing in science once again. Okay, so that was fun while it lasted. Natural log functions. Again, these should not throw you off. They are still log functions. So they still have the same critical points of what? 1, 0, and no, the natural log has a base of log base E of x, right? So it's E, which is 2.7. So if that's 1, 2, 3, 2.7 comma 1, and still the same asymptote. So we should not be thrown off in any way when we get a natural log graph. It is still a log graph with the same critical points as every other one. Okay? Same asymptote, same critical points. Stephen. Well, gave you, and I'll go over it again because I don't know if we rushed it. We probably. Well, let me back up to the definition, which I thought we did the other day. Where is this? Yeah, this one. With that whole PERT formula concept. As we continue to compound by quarterly, 4, monthly, 12, weekly, 52, daily, 365, as this n value approaches infinity, okay? Take this portion of that function, and as n approaches infinity, this number approaches this Euler's number. Correct. And therefore, when we get to continuously compounding, we just straight up use a base of e. Okay? Because we're compounding constantly, so an infinite, essentially, number of times. Well, I don't know if that's why it was invented, but I think that sort of that number. I don't really know the history of it. But someone very smart found that number. We can investigate that. I honestly don't really know the full history. I just always found that piece of information interesting. Like, who is that much of a genius that figured that out, A? But I feel like that may not have been the actual origination. I will look it up if we have time, because it's a great question. I'd like to know. So let's get through this, and then we'll hop on the most reputable source of all, Google. Oh. Okay. So again, with domains of natural log functions, they are still log functions. You cannot take the log of a negative number or of a 0, so you can only take the log of a positive. So this 3 minus x has to be positive. So solve that, add x to both sides. 3 has to be greater than x. In other words, x has to be less than 3. From a transformation perspective, let's talk about this one. This is the same thing as, to put it in a more conducive order, negative x plus 3. The order of transformations in a case like this, I do not believe you talked about last year. I think we talked about it already at the beginning of this year, though. When there are multiple horizontal transformations, what do you have to do first before you can, do you remember? Well, so what would you do, Josh, first? Let's see. Okay, so it's a vertical asymptote, and you're reflecting it horizontally, so it ends up being itself, right? And then you... Right, but that's not where the asymptote is. Its x is less than 3, so the asymptote should end up at 3. So something a little twisted happens with horizontal transformations, especially when you're dealing with 2 of them at once. Stephen? Yes, you have, okay, so if there's ever a combo of a horizontal stretch, reflection, compression, you have to factor that out first. So you would rewrite this as the natural log of negative x minus 3. And then, typically we follow order of operations, right? So we would subtract the 3 first and handle that and then negate it. However, all things horizontal happen backwards, right? Remember that. So, in fact, we are going to negate first. So we are going to do the flipping first. So think about your horizontal or your vertical asymptote flipping. And then it shifts right 3 units and puts it where it should go. Okay? Your critical point 1, 0 is going to do the same thing. So think about 1, 0, which would have been here. It's going to flip first to negative 1, 0, and then shift right 3 units. 1, 2, 3. So it ends up here. And your third critical point was E1, right? So 2.71. That's going to flip first and be negative 2.71, and then move 3 units to the right, which is going to be at like 0.3 and 1. So your function is going to look like that. Okay? Algebra 2 leaves, you do horizontal movements of all types, but if you looked back, and you probably wouldn't have realized it last year, you probably never did a stretch compression reflection paired with a shift. And you knew about doing the order of operations backwards too. She talked about all that. Yeah. We did. I think we did talk about it this year because it is an advanced concept, because it would be, think about transformations in Algebra 2. All of transformations is pretty brand new to you. If we added that dimension onto that for the first time when you're learning it, you'd be head spinning. Now that you have a good base with transformations, we kind of give you a little bit more detail, and really it's the rest of the detail about what happens in a case like that, because it's kind of twisted. So you can see, though, based on how I came up with my domain, given that you can only take the log of a positive, and then doing the graph transformations, how that matches up. Because your instinct would probably have been wrong, as we saw with at least Josh's anyway. But that's because it works backwards. Okie doke? Any questions on that? Okay. This one, what are your thoughts? Think about the fact that this is the natural log of x minus 3 squared, and what you think that's going to do. You might have some bonus points up for grab here because this takes some thought, but I think that you can do it, and I need to motivate you to try. So there's my motivation. Bonus points on the line. For a good explanation of what this squared thing in here is going to do. Connor, pick a number between 1 and 25. Pick an integer between 1 and 29. Nathan Zorn?
Never said.
Any idea what the square is going to do? Did you even take a minute to think about it? Stephanie? Nope. Lily? Josh? I like your thought process because you see a squared, so you're thinking bounce, like a degree of 2. Not quite, but I like where your head's at, so I'm going to give you 1. You're right, it is. Alyssa? You don't have your calculators out. You're not cheating, are you? Liam?
No, I'm not.
Liam is disqualified.
We're gonna get
I wasn't? I don't know. Alyssa? Very good. She's getting another one. Did you hear that over there, Nathan Zorn? What'd she say? Summarize. Correct. What? You were, yes, you were on the right track. So here's the thing. Normally with a log function, as you see, you have an asymptote, and then the graph only exists on one side or the other, because you can't take the log of negative numbers. So this was a parent graph. But here, because you're squaring this thing, it will always be positive. The only thing, except for when it equals 0. So it will always be positive when you square it, unless it equals 0. So that is the only point we have to ditch, right? That's where our asymptote is going to be. What x value will make this 0? 3. So you can't have the log of 0, so you'll have an asymptote at 3, which should make sense because that's the way this graph would be shifted anyway. So here's our parent graph. Let me get this down. The parent graph, P of x, is different. It's x squared. And it's actually kind of double-sided on both sides of the asymptote. This asymptote's right on the y-axis. This one has been shifted right 3. I actually don't know I think I know what the parent graph looks like, but I'm not positive. Well, because you look at your calculator. Oh, you didn't? I think it's going to be like this, but I'm going to do something to double check here in a minute. The first thing I'm going to do is think about my y-intercept. When x equals 0. 0 minus 3 is negative 3. Negative 3 squared is 9, right? 2.7 to approximately what power is 9? 2-ish. And would you agree that my y-intercept is 2-ish? Okay. My x-intercept when y equals 0, right? If that equals 0, this is where you'd have to follow your translation rule. Look up at the board. It would be your base of e raised to the 0 power equals x minus 3 squared, right? Which is going to be 1 equals x minus 3 squared. Which when you square root both sides, you're going to get plus or minus 1 equals x minus 3. When you add 3 to both sides, you're going to get 3 plus or minus 1 is your x-intercept. So that's an x-intercept at 4 and at 2, which is equidistant on either side. There's my one at 2. Should be a little bit there. There's my x-intercept at 2, and here's my x-intercept at 4. Do we follow? So now I'm positive. I was pretty sure, but it was a gut feeling. It wasn't for sure. Now later in the day when I teach this 2 more times, I'm going to pretend like I don't know, even though I know. But for you guys, genuinely, I didn't know because I haven't looked at this. All right? So, but the degree part, that whole bouncing concept, right? Your asymptote. If your asymptote has a degree of 2 or 4 or 6, we get the behavior headed towards the same infinity on both sides. Right? So there's a lot of consistency here with the asymptotic behavior. You good there? Yeah, Lily. I'm wrong? Oh, that could be. It could be a glitch with order of operations in your calculator. So your calculator might be taking the natural log first and then squaring the answer, as opposed to taking the natural log of... So you put it in parentheses when you type it into your calculator. Oh boy. Yeah. I'm glad you brought that up, Lily. Why? Why would the calculator, I wonder? So I put the entire thing. We're taking the natural log of the entire thing. We're not taking the natural log of x minus 3 and then squaring that.
If you take out the outer parentheses,
Yeah. Does that make sense, Lily? Okay. So I'm gonna ask more about that. We'll see if I have to look more in what is acceptable in math. Part of me wonders why the calculator wouldn't. Why would natural log come before squaring?
because it's a...
I know, but nothing comes before exponents.
Well,
I'm just wondering if when I wrote this, I should have put these in parentheses.
well, maybe it tells the natural log is exponents before the square root in terms of the actual order of the equation.
Well, the P step in parentheses just means simplify what's within the parentheses. That doesn't necessarily mean do the natural log of the... Nathan? In the exponential step. That's what I'm thinking.
Yeah.
Logs are exponents. So I'm thinking there's something to that.
Because it...
But let me ask. I'll see what Mr. and Mrs. Hill think. The three of us will discuss and we'll decide what we think. If the calculator is wrong or if... We'll see. Basic properties. We talked yesterday. The log of 1 is always 0. Now, given that the natural log has a base of e, the log with a base of e is 1. The natural log of e to the x's and the e to the natural log of x is x. So we remember those kind of shortcuts to help us save time. And the last one. Oh, this is a 2-second problem. The reading is going to take longer than the problem. Do it on your own. Ready, set, go. Calculator question. Josh, no one's going anywhere until I see this in your calculator. Tell me when you have it and I'll come over and check it. You got 40.82? Let me see what's going on. I know, but